So I was asked on Twitter to calculate the number of SARS CoV-2 particles, the particles that cause COVID-19, how many there were in the world. And so I did the calculation, and it turns out that there are few enough to fit inside a regular can of Coke.
In all the world?
In the whole world. In the whole world, you can fit it inside a single can of Coke. So I did it's a rough back of the envelope calculation. So I'm open to people disagreeing and saying, well, it's way more than that or it's way fewer. But this sort of estimation is called a Fermi estimate. It's named after this physicist, Enrico Fermi, who did loads of these sorts of calculations. He was interested in estimating things. His most famous one was probably when he calculated the energy released by an atom bomb that was detonated at the Trinity nuclear test. And he did this by holding a piece of paper and dropping it during the blast and calculating how far the piece of paper moved. And then he used all sorts of physics to try and calculate that there was about 10 kilotons of TNT equivalent energy released during this atomic bomb. And actually they calculated later using much more accurate calculations that it was around 21 kilotons. So it was pretty close, and well within an order of magnitude. So that's what these sorts of calculations are all about. So you've got to start by thinking about how many particles there are in the world at any one time, and then once you've figured that out, you need to know how big they are. The first part of the calculation means calculating how many people in the world are infected at any one time point, and then also calculating how many virus particles those people have in their body at any one time. So in terms of calculating the total number of people in the world that have got COVID-19 at any one time point, there are various estimates. I use a website called Our World in Data. They estimate that around 500,000 people in the world are infected, newly infected each day with COVID-19. And so that is clearly going to be an underestimate. And the reason for that is that, firstly, loads of countries are not going to be testing everyone. They're not going to be testing as much as countries like the UK or the US are testing. But also, we think that about a third of people that get COVID-19 are asymptomatic. So they don't even know they've got it. So they don't even know to go and get a test. So in order to figure out how many people are actually infected every day, you need to do a bit of modelling, a bit of statistical modelling. So there's a group called the IHME, the Institute for Health Metrics and Evaluation, and they have modelled this using statistical modelling and also using mechanistic modelling, so these compartment-based models that you might have heard of, these SIR models, which I know there's another number file video of with Ben Sparks, so go and check that one out. So they've used a combination of these models, and they've estimated that around 3 million people a day are probably getting newly infected with COVID-19 each day, so quite a large number of people.
Okay, so that's 3 million new a day, but there are people who already have it, so...
Right, exactly. So there's 3 billion people new a day, and then we've got to think about how many virus particles each of these people has got, and then we've got to think about how long they're infectious for. So we need two things for that. We need to know what their peak viral load is, so how many particles they have when they're at their most infectious, and also we've got to know a distribution for how infectious people are. So they'll start off not having very many virus particles in their body, but then as the virus particles hijack their cells and turn them into virus-making factories, then they'll increase the number of virus particles they have in their body until a point where it peaks, and that's the peak viral load, and then it'll start to decline as the body starts to get on top of the virus. So I found a paper which estimates the peak viral load in humans to be between 10 to the 9 and 10 to the 11 particles. So that's 1 billion to 100 billion particles for each person. And the way they did that is by looking at tissues from monkeys. So they looked at respiratory and digestive tissues, so lungs and the way that your food gets through your body, which is where SARS CoV-2 is most likely to be. And they calculated the concentration or the density, the number of particles per unit mass of that tissue. And so for respiratory tissues, so things like the lungs and the trachea, they found that there were between 10 to the 6 and 10 to the 8 particles per gram. So that's between 1 million and 100 million per gram. And then they took those estimates and they worked them up to see how much would be in a human. And so they thought, well, the most important tissue in human, which is the biggest contributor, is going to be the lungs. And there's about 1 kilogram of lung in a human, apparently. And so they scaled that figure up from 10 to the 6 per gram. They scaled that up to 10 to the 9 per kilogram, if you like. So on average, a human has between 1 billion and 100 billion SARS-CoV-2 particles at peak viral load in their body. So now you need to know this viral load distribution, right? So I'll show you what it looks like. This is the viral load distribution on the y-axis, and on the x-axis, this horizontal axis, I've got time looks something like this. So it goes up like this, it rises to a peak around 6 days, and then it falls off quite slowly like that. So this is about 6 days here. And so I guess what we need to figure out, who's infected at any one time, we need to think about who got infected yesterday and what their viral load distribution is, who got infected the day before and what their viral load distribution is, and so on, all the way up to the end of this distribution. So people that got infected, say, yesterday, they will have a relatively low viral load. People who got infected the day before will have a slightly higher viral load, and so on, until we get to up to 6 days, when we'll find that people have their peak viral load, and then people who got infected 7 days ago and 8 days ago and 9 days ago and so on throughout the rest of this distribution, they'll have a lower viral load. And so we need to think about, technically, mathematically, what's called a convolution. So we need to be thinking about how many people were infected 2 days ago and multiply that by how high their viral load would be now. How many people were infected 3 days ago and multiply that by what their viral load would be now. How many people were infected 4 days ago, and so on. So that's technically called a convolution. It doesn't really matter how you think of it, but the point is that we have to add up all these different viral loads of people that got infected before today, thinking about how infectious they are today. And when you do that, thinking about 3 million people being infected every day on average, then you can work out that there are 200 quadrillion virus particles in the world. So that's a 2 with 17 zeros behind it. So that's roughly the same sort of order of magnitude of the number of grains of sand in the world. It's probably about an order of magnitude less. But of course, we should caveat that by saying that that number of grains of sand in the world calculation is also a Fermi estimate, so it's not a sort of accurate. And again, so I'm more than happy for people to say that this is too high or too low based on some different estimates. So for that calculation there, I used the middle of the peak distribution of the viral load. So I used, instead of, it's between 1 billion and 100 billion, so I used 10 billion, which someone will say, well, that's not the average, because if you add up 1 billion and 100 billion and divide it by 2, then that's about 50 billion. But I'm talking about a different average. I'm talking about the geometric average, where you multiply two numbers together and you take their square root. So that's what I've used. But of course, in that estimate, there's 2 orders of magnitude already. So you could argue that it's 10 times bigger or 10 times smaller already. But in the middle of that estimate is around 200 quadrillion virus particles.
200 quadrillion. All the sand on Earth. Sounds like a lot to me. Yeah,
it's a huge number. But then when we're thinking about calculating the volume, we've got to remember that each of these virus particles, these SARS CoV-2 particles that cause COVID-19, they're incredibly small. So again, I looked up an estimate for the diameter of a SARS CoV-2 particle, and they're roughly spherical. That's what we'll assume. They've got these spikes sticking out of them, these spike proteins that you'll have heard of. But the estimate is around between 80 to 120 nanometers. So in the middle there is an estimate of 100 nanometers. So that's the estimate that we'll use. And once you know that estimate, then you can use relatively simple mathematical formulas that people have met at school probably. So the formula for the volume of a sphere is 4/3 times pi times the radius cubed. So the radius is half the diameter, so it's about 50 nanometers. And so when you plug into that formula, you find that firstly, SARS-CoV-2 particles are incredibly small. They take up so little volume, but of course there are huge numbers of them. And when you multiply the number of virus particles, this 200 quadrillion, by the tiny volume, you get something which is actually a tangible size. It's about 120 milliliters. And actually, so that could fit in about half a can of Coke. That's not quite the end of the story though, because spheres, we know, don't pack together nicely like cubes do, or like bricks stacking on the wall. Actually, the way to think about spheres is thinking about when you go into a greengrocer's shop, thinking about a stack of oranges in a pyramid maybe. And you think of those and you think, well, not all of that is made up of orange. Some of that is empty space. So actually, the best you can do is packing them like this pyramid of oranges to pack spheres together. And that only gets you a volume of about 75% of that volume of pyramid would actually be oranges, and 25% of it would be empty space. So we have to account for that empty space when we're putting these particles together inside the can, and that would probably increase the volume to about 160 milliliters. So still enough to fit in a can of Coke. Other people might argue that you're never going to be able to stack these spheres perfectly, and really you should be using random closed sphere packing. And actually that does even worse in terms of the volume. It's only about 60% there. So if you were to use that estimate, it would probably be about 200 millilitres of SARS-CoV-2 in total, but still enough to fit inside this can of Coke.
How many millilitres in a can of Coke?
So there's 330 in a can of Coke, so it would be about 2/3 full, even at the upper end of this estimate. Again, I used that middle estimate for the peak viral load. Even if it were 10 times bigger, then it would probably be about 2 litres, and then at least it would be enough to fit in a 2-litre Coke bottle, if not a can of Coke.
What about other stuff? What about COVID that's not in humans? It's like sitting on surfaces and in the air and animals?
Yeah, it's a really good point that not all COVID is inside humans. So we think that COVID doesn't last very long on surfaces, so I've deliberately neglected that. There are animal reservoirs, but again, it's so hard to quantify that, that I haven't put that into the calculation. But yeah, so I've just considered the COVID that's inside humans, but certainly there's probably an underestimate from that point of view.
Kit, I'm assuming another thing you didn't take into account with your calculation is how well these things do pack together. Are there any repulsion forces involved? Do those spikes cause problems?
Yeah, absolutely. So I haven't taken into account any of the chemistry of the problem. And people have been asking, what would it be like if you could get them all? Would it be a liquid? Would it be solid? And I honestly don't know. I have spoken to a couple of chemists about this, but they also think it's quite a hard thing to try and understand. But yeah, certainly there would be perhaps repulsive interactions between these particles, which might make it a slightly bigger volume again. But yeah, I haven't taken the chemistry. It's more of a physics and mathsy point of view, this one.